Welcome to Lesson 11.4, Fundamentals of Probability. In this section, you may see terminology that may look familiar, as well as terminology that may look new. My hope is that this section will clear up anything that is confusing to you as you are trying your problems in 11.4. When we talk about probability, please recognize that your answer will always be between 0 and 1. If you look at the scale to the right, you can see that 0 means that the event is impossible. It will not happen, right? And that scale goes all the way up to 1, which is the same as 100%, right? And that is that the event will certainly happen, that it will happen for sure, beyond a doubt, right? Most of our answers will fall between 0 and 1. Most likely you will give your answer as a fractional answer, right? But these can also be converted to decimals or percentages. When you're computing theoretical probability, we're looking at an event, E, that has the number of events equally likely outcomes, and its sample space has N of S, right? The number of the sample space equally likely outcomes. The theoretical probability of event E, denoted by the probability of E, is, right? So it's a fraction. It's the number of outcomes in the event that they're asking you for, divided by the total number of possible outcomes, right? So when we're looking at theoretical probability, we're not looking at anything that has actually happened. We're not looking at outcomes that, you have rolled the die or flipped the coin or collected data. You're looking at it as theoretical, right? So when we roll a six-sided die, like in letter A, right, we expect that each side is equally likely. So when you're asked to find the set of equally likely outcomes, what you're being asked to do is to list everything in that sample space, right? So what are the things that can happen? You can roll a 1, a 2, a 3, a 4, a 5, or a 6, right? So we know there are 6 total outcomes, right? The first question asks you to find the probability of rolling a 2. So when we look at the set of outcomes, the likelihood of rolling a 2, well, how many 2s are there, right? There is 1. So when you look at the definition, the number of outcomes in the event E, right? How many outcomes will give us rolling a 2, right? And that will be 1 over the total number of possible outcomes. So we know that there are 6 possibilities here, and that is our denominator, 1 over 6. What is the probability of rolling an odd number? Right, so our numerator is always the number of outcomes in the event. So where do we see our odd numbers? Well, there they are, 1, 3, and 5. How many are there? That's going to be our numerator. There are 3, 1, 3, and 5 possibilities. And the total number of possibilities, again, we counted them, 1, 2, 3, 4, 5, 6, is 3, 6. And you'll always put those in lowest terms, right? 1/2, a 1 out of 2 chance of rolling an odd number when you roll that six-sided die. All right, the probability of rolling less than 12, right? So when I look, my possibilities are 1, 2, 3, 4, 5, 6. That's all 6 of them, okay, out of the total 6. So here's an example where the probability is 1. If you roll that die, it is guaranteed that the number will be less than 12. right? Since the only options are 1, 2, 3, 4, 5, and 6. Compare that to the probability of rolling a number greater than 7. Well, our only choices are 1 through 6. So the likelihood of rolling anything greater than 7 is 0 out of the total, which is 0 out of 6. And that probability is 0, right? It's impossible. We are guaranteed that, right, nothing will be greater than 7. Alrighty, good job. Keep going. A fair coin is tossed 2 times. Right, so what are the possibilities when we toss that coin twice? Right, so let's see. I can get a heads and a heads. I can get a heads and a tails. Right, or it could be the reverse of that. I could get a tails first and then a heads. I can also toss that coin and get tails, tails. So there are 4 options here, right? 4 possibilities of things that could happen. So most likely in my math lab, they're giving you these, but it's nice to talk through them and make sure that they make sense. All right, the first question asks you to find the probability that there is exactly 1 tail. Right, so when we look at our equally likely outcomes, exactly 1 tail, well, let's see. It happens here and it happens here. Right, in the first one, there is no tail, and in the last one, there are 2 tails, right? So that's 2 out of the total possibilities, right? And if you count up the number in our sample space, we have 4. So 2 out of 4, which is 1 out of 2, right? You have a 50% chance of rolling or tossing that coin and finding exactly 1 tail. The probability of exactly 2 tails So exactly 2 tails, it looks like that only happens when I get tails and tails, right? So that would mean that that is 1 out of the total, which is 4. So a 1 out of 4 chance, or a 25% chance that you will toss the coin and you will get 2 tails exactly. Alrighty. So those of you that are comfortable with decks of cards, you may not need this chart, but it is nice to have. So if you don't have this, feel free to copy it or color what you need to color, and tell yourself and learn about the suits, right? Which we have clubs, diamonds, hearts, and spades. And then our cards go from an ace through a king, right? So an ace through 10, and then our picture cards, jack, queen, king, right? There are 52 cards in a deck, and they are divided evenly amongst these 4 suits. So let's see, our next question says you are dealt 1 card from a standard 52 deck. Find the probability of being dealt a queen. Okay, so when we look at the deck, we see that here are our queens. We have a queen of clubs, we have a queen of diamonds, a queen of hearts, and a queen of spades, right? So we have 4 queens in a standard deck, and that is out of the total number of cards, which is 52. Right, so put that in your calculator, put that in lowest terms, divide by 4, and we have 1 out of 13. You have a 1 out of 13 chance of pulling a queen. All right, how about the probability of being dealt a spade? Okay, so when we look at all the spades, all right, we can erase this here. Let's see, here's the spades. All right. My friend likes to call them shovels. And here's all of the spades, right? So if you count those, right, count all the spades right there, you would count 13, and that would be out of the total deck, which is 52. 13 out of 52, and we are at 1/4, or 25% chance that you would be dealt a spade. Alrighty. What's the probability of being dealt a red king, right? So now we're being specific. If we look at our chart, let's find all the red kings. So let's see, here's kings right here. And I have king of diamonds, and we have a king of hearts, right? So there are 2 of those total out of the whole deck of cards, which is 52. 2 out of 52. Right, that would give us 1 out of 26. All right, so I hope this is making sense. If not, feel free to reach out. Okay, this chart is set up nicely for you. They've given you all the possibilities, and the way this is read is like this. We're looking at a single die, right? And it's 6-sided, and it's rolled twice. So here's the first roll, right? The first roll might be a 1. Well, what about the second roll, right? The second roll may be a 1. And so they list that possibility in the chart as 1-1, right? So if I just pick something else randomly in the chart, right? Let's say I'm looking down here. My first roll might be a 6. My second roll might be a 3, right? And so they list it as 6-3, right? So here's everything that can happen when you roll that same die 2 times. All right. So let's take a peek at the probability, right, of getting 2 numbers whose sum is 5. Right? So I need to look at that chart, and I need to find where all the rolls add up to 5, right? So 1, 1, no, that adds up to 2. 1, 2, that rolls and adds up to 3. I'm looking for 5. So we know 5 would be, let's see, 1 with a 4. And don't forget, it could also be 4 and then a 1. So that's 2 already. And what else? It could be a 2 and a 3. There it is. Right? If I did it the other way, it could be a 3 and a 2. Right? And that would be it for the sum is 5. How many possibilities here? That's 4, right? Out of the total, right? How many possibilities with a 6 by 6 here? The total, if you counted all these, would be 36 outcomes, right? 36 possibilities. And so the probability is going to be 4 out of 36, which is the same as 1 out of 9. Alrighty, how about the next one? What's the probability of getting 2 numbers that are identical, right? Okay, so let's erase what we've done so far. Identical, right? We know that's going to be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. That's going to give us 6 out of the total, which is 36. And that leaves us with a 1 out of 6 chance of rolling two numbers that are identical. So this is what theoretical probability looks like, right? Everything has an equally likely chance. Now let's compare that to computing empirical probability, right? So applies to situations in which we observe how frequently an event occurs, right? So the probability is defined the same way. It's instead of being the equally likely, it's actually the observed number of times that E occurs over the total number, right? So the idea is the same, but for instance, I'm looking at a chart in letter E, right, that has people categorized, and they have them categorized as married, never married, divorced, widowed, and then they break them up between male and female, right? And so there's not an equally likely chance of this happening when a group of people. This is actually the data, right? And that's why it's empirical. So let's look at our first question. If one person is randomly selected from the population described, find the probability that the person is female. Right? So the probability that the person is female. We're not concerned at all about the status, married, never married, divorced, widowed. We're just looking for the number of female participants over the total. Okay, so take a look at the chart. Find what you're looking for. Right, so here's the female category, and then it breaks it up. Right, we're not worried about that. We just want to know the total number of female, and that's 124. And what would that be out of? That would be out of the total number of people who are getting categorized here. And the total number, if you look under totals, is going to be 242. Right, so 124 divided by 242, if you put that in lowest terms, that's going to give us 62 out of 121. Right, so we divided everything by 2 here, and that's what we have in lowest terms. Now compare that to the probability of never been married. Okay, so let's get rid of all these. All right, so never married, the categories up top. We're looking for the total of never been married, right? And that's 74. And that's out of the total population, right? And we already said when we looked at the chart that the total number of participants is 242. When we put that in lowest terms, we're at 37 out of 121. Divide both the numerator and denominator by 2. Alrighty. Let's look at the next question and the last. The table shows the distribution by age and gender. Okay, so we're looking at male and female of the 31.3 million people in a certain region who live alone. Okay, so we're looking at how they're broken down by ages and male and female. Okay, and so we also know that this is in millions, right? Because it says 31.3 million people, and so that's the total right there. So we know the rest of this is also in million. So use the data in the table to find the probability that a randomly selected person in the region is a woman in the 18 to 24 age range living alone. Okay, so when we look at the chart, we're looking for female, right? And in that first age bracket, so female, and in that first age bracket, we're at 0.6 million. And out of the total that were in this study, we're at 31.3 million. Okay, and so we want to simplify that. We know million divided by million, right? We are okay on canceling all those zeros. And so we're left with something that looks like a decimal divided by a decimal, right? So one way to simplify that, you can do it in your calculator, but if I multiply by 10, the numerator and denominator, that would move the decimal point over one time. Remember, I always have to do the same thing to the numerator and denominator of a fraction. So I would be left with 6 divided by 313. So 6 out of 313 would be a female living alone between the ages of 18 and 24, right? So if you're saying like, is that really common? That's approximately equal to 0.02, right? And that would be, if I move it 2 times to the right, about 2% of everyone living in a certain region. Okay, so I hope that that's been helpful and that makes sense. Please reach out to me with questions when you're filling this in or have some homework questions.